Okay, so here's another problem. So we've got hydrogen plus iodine going to hydrogen iodide. We're given Kc. So Kc is 54, so that means that will be probably a few more products and reactants at equilibrium. Not a dramatic amount, maybe. And we're told the initial amounts of hydrogen iodine and hydrogen iodide and the total volume. So probably the easiest thing to start off with this problem is to convert those amounts into moles. Those amounts into concentrations. So the concentration of H2 is going to be 0.714 moles over 2.4 liters. And if you do that, you get 0.298 moles per liter. And we can do the same thing for iodine. And if you calculate iodine, you get 0.41. And hydrogen iodide, if you calculate that, you get 0.369. And so those are our initial concentrations. So the question is, in our ice chart, which way is this guy going to shift? Because if you look at it, we've got both reactants and products present. And so the question is it going to go and make more products, or are the products going to turn back into reactants? And so in order to figure this out, we're going to have to calculate something called QC, the reaction quotient. And so QC is basically a test to see if we're at equilibrium. And if we're not at equilibrium, we can go ahead and we can calculate which direction things are going to shift. And so to form Q, you basically just take the expression for K, and instead of using the equilibrium values, you just go ahead and use the instantaneous values of these guys. And so if you go ahead and substitute all those in, so the initial concentration of HI is 0.298 molarity, but remember in K and Q we don't write units, so we'd square that. And the concentration of hydrogen is 0.41 molar, and iodine is 0.369 moles per liter. And so that gives us a value for Q, the reaction quotient, of 0.587. Now you compare that to K. K was 54.3, so clearly we're not at equilibrium. And what else can we say? To be at equilibrium, QC has to go up, because QC and KC are the same at equilibrium. So what does that mean? How does QC get to go up? Well, Q, like K, is always going to be something about products over something about reactants. So the only way to make Q bigger is P's got to go up, the products, and R, the reactants, have to go down. And so if we look at our equilibrium, reactants forming products, then basically for P to go up at the expense of R, we are shifting from left to right. So that means that we're using up reactants and we're making products. So that's good. So that tells us that right off the bat, we are causing a shift from left to right. And when we fill out our ice chart, we can go ahead and take this direction into account. So let's go ahead and set up our ice chart, right? So we've got our initial, our change, and our equilibrium. And we find these concentrations. So this is 0.298 moles per liter. Iodine is 0.410. Hydrogen iodide is 0.369. The change, well, we calculated a left to right shift by looking at Q. So hydrogen and iodine are going to go down, and hydrogen iodide is going to go up. And don't forget, because there's a 2 here, that means that the loss of one of these is going to make twice as many of these. So now at equilibrium, we can just go ahead and we can sum the initial with the change. So 0.298 minus X. For iodine, it's going to be 0.41 minus X. And for HI, it's going to be 0.369 plus 2 times X. And all of these ice chart problems typically work the same way. We write down the ice chart, we fill out as much as we can, and then we go ahead and write our expression for K, and we try and solve. And so KC is HI squared over H2 times by I2, and all these are equilibrium values. And we have all of these in terms of x's, and we know Kc is 54.3, and so we can basically just plug everything in. 0.369 plus 2x squared over 0.298 minus x and 0.41 minus x. Now the last problem we looked at, right, we tried to solve this and we said, well, the right hand side's a square on the top and the bottom. It's a perfect square, so we can just square root and it's much easier to solve. Unfortunately, we don't have a perfect square. So what that means is that we're going to have to cross multiply and FOIL out and bring all the x's to one side and solve the quadratic equation. So that's probably our next game. Alright, so we're going to have to go ahead and cross multiply and expand and FOIL and all that good stuff and figure out what x is equal to. So our first thing is to bring the bottom of one side to the top of the other. So that's 54.3 times by the bottom, like so. And then we can FOIL these terms. So when we multiply them together, we get the first, the outer, the inner, and the last two. And we can FOIL this out fairly quickly. So there we FOILed out the first two of the four terms. So the first term, 0.298 times 0.41 is 0.122. The outer, 0.298 times minus x, well, that's just minus 0.298x. Okay, so we FOILed out the left-hand side, and we can go ahead and do the same for the right-hand side as well. We can rewrite the right-hand side, 0.369 plus 2x all squared, as follows. And then we can proceed to FOIL out this side the same way we did before. Except we should probably move things up a little bit. Okay, let's FOIL. So they were just FOILed the first two terms, and now we can FOIL the last two terms. And so now we've got the complete expression for the right-hand side. Now the left-hand side, we've got a little bit more work. We've got to go ahead and maybe we can collect these terms together, and then we can distribute the 54.3 over. And on the right-hand side, we can collect these terms together. So let's go ahead and just kind of clean all that up in one fell swoop. So here's what the left-hand side looks like, and now we can work on the right-hand side. And this is what the right-hand side looks like. Okay, so it's probably worth making sure that you can do all the algebra by hand. On the exam, it kind of takes a while if you get stuck on these problems. Alright, so now what we want to do is we want to get all the x squareds to one side. So that 4x squared on the right-hand side, we're going to subtract that from both sides to get it all the way on the left. This x term here, we're going to subtract it to push it to the other side. And this 0.136, we're going to subtract it from both sides to bring everything over. And that way we'll get x squareds and x's and constants equals 0. So let's try that. So that gives us this expression here. And what's the nice thing about this? Well, this, and notice the way I've arranged it from higher powers of x to lower. This now looks very, very familiar to you, or at least it should. So this looks just like our friend the quadratic equation. So we can write it ax squared plus bx plus c equals 0. And once we write it like this, we know that x is minus b plus or minus root b squared minus 4ac, all divided by 2a. And we have to identify, what's a, what's b, what's c. So a is positive 50.3, and b, we have to watch out here, so it's negative 39.9, and c is positive 6.48. And so we're going to plot those in our expression underneath, and that should give us what x is equal to. So let's go ahead and try that. And so collecting terms together, we've got 39.9, and that was a negative, but we flipped the sign, plus or minus the square root of 288 divided by 2 times 50.3. So that's going to give us two solutions, right? And so we're going to end up with two different solutions. And if we go ahead and we do the math, we get either 0.566 or the other solution is 0.228. And so the question is, how do we know which one is correct? Well, normally in these problems, mathematically, of course, both are fine, but we find that physically there are restrictions on solutions, and so not all of them are acceptable. And the easiest way to figure this out in this problem is we'll look at the hydrogen concentration. It's 0.298 minus x. Now, if your value of x you take to be 0.566, that gives a negative concentration for hydrogen. And so we know that can't be the correct one. If we plug in the other one, the 0.228, in place of x, we'll see a positive concentration. And so we know that negative concentrations are impossible. Positive concentrations are just hunky-dory. So that means if we take the positive concentration, if we take this right-hand value of x, we can calculate it, and it ends up being 0.070. And at the end of the day, we can put our concentration units in. What about the concentration of iodine at equilibrium? Well, iodine was 0.41 minus x. And again, if we substitute in for the physically reasonable value of x, we can get an iodine concentration that's 0.182 moles per liter. And again, the hydrogen iodide equilibrium concentration, well, that's 0.369 plus 2x. And if you substitute in the value of x above, you get 0.825 moles per liter. So notice those all came out positive as we'd hoped for. So how confident are we that we did this correctly? Well, maybe not very confidently at all. So what's the best way to check? The best way to check is to look at the expression for Kc and throw those values back in and pray to the chemistry gods that you're going to get the correct value for your equilibrium constant. And so we know that we're aiming for 54.3, and we're hoping that it's going to give us that same value. So let's check. So if we plug those values in above, HI was 0.825. We're squaring that. H2 was 0.07. And we're multiplying that by iodine, which was 0.182. And when we calculate that, that gives us 53.4. So, probably close enough. So why isn't it exact? Well, if you notice, all the way through, I was rounding off. And so we've accumulated a good amount of round-off error. I would say as long as you're within 10%, you're probably pretty comfortably close.